Okay, so we've got a ladder, AB, has mass M and length 6A. The end of the ladder is on rough horizontal ground. The ladder rests a fixed smooth horizontal rail at point C, and the point C is at a vertical height of 4A above the ground. The vertical plane containing AB is perpendicular to the rail. The ladder is inclined to the horizontal at an angle of alpha, where sine alpha is 12/13. The coefficient of friction between the ladder and the ground is mu. The ladder rests in limiting equilibrium, and the rod is modeled as the ladder is modeled as a uniform rod. Right, so let's have a read again, and then we can start putting things in. So we've got a ladder of mass M, and we know this is a uniform rod because we've read it once. So therefore the weight, which is capital MG, will go in the middle. So this distance is 3A here. And then we know it's on a rough horizontal ground, so the ladder wants to slip to the left, and so the friction, because it's rough, will go to the right. And then you've got reaction here. This is on the ground. The ladder rests against a smooth horizontal rail. Okay, so there's going to be also going to be a reaction over here. And I usually call that N. And it's smooth, so there's no friction on that rail. The point C is a vertical height of 4A, and then sine alpha. Okay, so let's do our triangle again. We know alpha. We know sine alpha is 12/13, so opposite over hypotenuse is 12/13, and that makes this 5. So cos alpha must be 5/13, and we know that sine alpha is 12/13, but let's just write that down anyway. And we also know that the coefficient of friction is mu, and it's in limiting equilibrium. If it's in limiting equilibrium, then we know friction is at its maximum, so F is equal to mu R. And it's modeled as a uniform rod. Okay, so good. Let's resolve. Now notice that you've got R and F and MG, which are in the vertical and horizontal planes. So we should only split, so we should resolve vertically and horizontally in this case. All right, so we're going to do two equations like that. I'm just going to write all my forces quickly and do this. Do my table. It's got MG and we've got N. So the only one that actually needs resolving, because the only one that isn't either horizontal or vertical, is N in this scenario. So you've got that, and you've got that, and you've got. Right. Now N needs its triangle. So we're basically, when you're resolving horizontally and vertically, you're basically finding, it's like finding the I and J components. So you draw horizontals and vertical lines. And it's important to put the arrows on there, because then you know the direction. That is important when we resolve, when we put it into our result equation. Now angles, Z angles, if you look at the Z angle here, so that means that this is alpha, which means that the inside angle is 90 minus alpha, and therefore the top angle is alpha. So the top angle is alpha. I've got N cos alpha next to it, and N sine alpha opposite it. So going upwards, I've got N cos alpha, and going to the left, my arrow is going to the right, so I'm going to put this as minus N sine alpha. Everything's in equilibrium, so both of these equations are equal to 0. So now I can just fill this in. So we've got R minus mg plus N cos alpha. Cos alpha is 5/13. So I'm going to have 5/13 times N. And that's equal to 0. And when I resolve horizontally, I've got F minus N sine, and sine was 12/13. So 12/13 N. And that's equal to 0. You'll notice that, and I know F equals mu R, but you'll notice that there's too many unknowns still. I'm going to need another equation. And that comes from taking moments. It makes sense to take moments about point A because there's two forces acting through A. Moments is calculated by doing force times perpendicular distance. So the first force that comes along the ladder is mg. So that's the force. Let's do that. Right, so this is the force. And the perpendicular distance is going to be the horizontal distance here. Now that horizontal distance, if I look at only my distance triangle now, just draw it over here. We know that the hypotenuse in my distance triangle is 3a. And we know this is alpha. And I'm trying to work out this length here, which is my adjacent side. So I can say that that's going to be 3a cos alpha. And that's my horizontal distance there. Now, my next force, there's no other forces until you get to n. And n's going to make it move, if you look at it, n's going to make it move anti-clockwise, whereas mg is going to make it move clockwise. And because it's going to make it anti-clockwise, I'm going to subtract it. So I'm going to subtract n, and it's multiplied by the perpendicular distance. Now n, because that n was a reaction force, it's going to be perpendicular to the surface. And therefore, the perpendicular distance is this length over here. Now, unfortunately, we don't know that length, so let's draw another triangle. This time, this length is unknown, but what we do know is that we know that the vertical length is 4a. And again, we know this alpha. Okay, so then we can say that sine alpha, because I'm using the opposite and the hypotenuse, sine alpha is 4a opposite over hypotenuse, and hypotenuse is what I'm trying to work out. So I could rearrange that equation to say that h is equal to 4a over sine alpha, and sine alpha was 12 over 13. And that's going to be my perpendicular distance for the n force. So I'm just going to write that as 4a over sine alpha at the moment. And now I've taken moments, right? Because I took it about a, I only had to consider the weight and the reaction force at the rail. And this is equal to 0. Everything's in equilibrium, so it equals 0. Now, if I look at if I look at this last equation, the moments equation, I can say that n is equal to. So I'm trying to show that the magnitude of the force exerted on the ladder by the rail at C is 45 over 169 mg. So I'm trying to find in what I've labeled as n. So I can say that that's mg 3a cos alpha. Cos alpha was 5 over 13. And that's equal to 4a n over sine alpha. I can cancel a's, so that's good. Now here I've got 15 mg over 13, and that's equal to 4n. I've still got this, sine alpha we know is 12 over 13. So let's just rewrite that. G over 13 is equal to, and if I make that over 12, let's rearrange this. And so if I take the 12 over and divide by 52, so times by 12, divide by 52, I make that, okay, so that gives me 45 over 169 mg, which is what I wanted to show. So I've done that, that's equal to n. Now that might seem a lot for 3 marks, but actually we only needed the moments equation. I did the resolving and everything, and hopefully that will help for part B. Right, hence or otherwise find the value of mu. Right, okay, fantastic. Now if I I've got my n value now, and I've got in my resolved equation, so if I look at my vertical, I've got, so you shouldn't use equals, colon, r minus mg plus 5 over 13 and then I can use my n value from here. So that's 45 over 169 mg, and that's equal to 0. And from that I can find out that R is equal to 1972 over 2197 mg. Okay, great. And if I then if I take my value of n and I sub it into my horizontal equation, I knew that from my horizontal that f was equal to 12 over 13n. So if I move the 12 over 13n to the other side, and n is 45 over 169 mg. And I know that f is equal to mu r, so mu times 1972 over 2197 mg equals, and then over here I've got my whole 12 over 13 times 45 over 169 mg. And if you rearrange that, you get mu as 135 over 493, which is 0.274. So that's the value of mu.